We're FRC Team 670 from Homestead High School in Cupertino, California. We'd like to present what we created to tackle the 2020 First Robotics Competition Challenge, Infinite Recharge. In this game, two alliances of 3 robots each perform tasks like shooting power cells, the yellow balls, into different goals, and climbing onto a tilting bar. These balls are compressible and have a dino-skin surface, meaning that they tend to stick to any surface they contact. These properties pose challenges that our design had to address. Because of that, one big design consideration was how to keep the ball moving, since otherwise it was likely to get stuck. In designing, we also had to work with size, height, and weight constraints. After considering some different options, this was the system design that we decided on. We went with a tall robot so shooting balls and climbing would be easier. This gave us room to individually store balls, but also meant that the path a ball takes from the ground to the shooter was going to be longer. Here's what a ball would see as it moves through the path in the robot. As you can see, there are many steps on this path that need to work together for the ball to be able to make it through. Let's take a look at the things that are keeping the ball on track and moving when everything's going well. First, we need to get the balls off the ground and into the robot, so we start with the intake. After being intaked, the balls pass onto 2 conveyor belts, moving them along the transition to the indexer. We had to add several measures to keep the ball on the path as it moves straight back. For example, we added a tunnel with brushes on the inside, which guide the ball towards the center and keep it from sticking. After testing, we also found that if the ball isn't fully centered and all the way back in the indexer could jam when it starts moving. So, we had to add 2 pistons centered on the bottom of the indexer. Their placement is carefully oriented so they punch the center of the ball, and this is timed to happen thanks to a time-of-flight sensor. The next step is the indexer, which can store up to 5 balls. The balls are separated by arms, which are spaced out and covered with rollers. There are a lot of these rollers all around the indexer, and they keep the balls moving and prevent them from sticking to surfaces and jamming. Balls are stored and staged, and when ready to shoot, the updraw runs to kick balls up to the shooter. While this is happening, the turret on our robot aligns to the target before the balls reach the updraw or the shooter, thanks to our custom Raspberry Pi-based vision system. When the updraw runs, balls travel up and into the shooter, which shoots them out as soon as the ball touches it. Now, this is the path taken by the ball when everything is working together well, but often that's not the case. Remember those sticky power cells? Sometimes they get stuck on things or moving parts and cause jams. When that happens, the entire system could stop functioning, as balls can't move from one point to another and the entire sequence is interrupted. In a competition environment, when we're on the field, we can't go in and reset the robot or interfere with it in any way, so although we tried to minimize the chance of jamming in our design, for example by adding rollers so the ball won't stick, it would also be great to automate detecting and dealing with jams when they appear. If something's stopping the ball from taking the good route, here's how we'll try to get it back on track.
A common place where jams happen is on the intake. If the intake is stuck, we don't have another way of obtaining balls, so it's essential that the robot can resolve jams automatically if they come up. To unjam the intake, we can run it backwards. But when should we do that? We need some kind of indicator so we can automate the process. We notice that when the intake is jammed, the current drawn by the motor controller spikes, and we can read this data in. So when we detect the current spiking, we can run the intake in reverse until the spike drops, and thus the jam is gone. Similar to the intake, balls could jam in the indexer too, and as it plays an important role in the transition of balls from the intake to the shooter, it is important to resolve the jams that come up in the indexer too. Primarily, we use the pistons to push the ball completely into the indexer to prevent or dissolve jams that occur in the bottom chamber of the indexer. However, if a jam occurs in a different chamber, it can be resolved by rotating the indexer backwards. This unjam indexer process runs only when its motor controller detects a spike in the current drawn, and for 150 cycles, which is close to a chamber or 72 degrees. After testing though, we had another issue. How do you determine if an observed current spike is actually a jam? It could be from just starting the intake, or it could have been a small spike from a ball brushing against something. So, we looked at how long the spike is present for by checking current values in a time interval. For example, if you're seeing a spike over 10 cycles, meaning that something is stuck, and if that's the case, we run the unjam sequence. Finally, if no jams occur, we use a computer vision system to track a target and aim at it by calculating the angle needed to turn towards the target when triggered.
To tackle the challenges posed by Infinite Recharge, we used our creativity to design, build, and test this robot. The many interconnected elements within the system meant we had to find creative solutions to keep it up and running, whether through automation or integrating unique design elements. Though we had to deal with problems and try new things through development, the end result is a robot whose many innovative parts work together, passing along the ball and accomplishing the challenge of the game.